is just a way of modeling the world around us. So wouldn't it be weird if all of the world's greatest art could only be made with black and white? You can kind of get a picture of what's going on, but if you really want an authentic replication of the world, you have to have color. Which is what brings me to physics. Physics is just another way of modeling the world around us. But instead of using canvas and paints and brushes, we use a lot of equations and oftentimes computers. So what if I told you that until recently, our most powerful computing tools were only modeling our world in 2 colors? When in reality, we know that our world is color. So we have to have quantum mechanics. That's the color in this analogy. Okay. So quantum mechanics is what governs our world at the smallest scale, the atomic scale. It's what determines how atoms come together to form molecules that could be the next life-saving medicine or world-changing material. And it's really weird. In quantum mechanics, particles can act like waves and interfere with one another from a distance, and waves can act like particles that are quantized. Furthermore, those classical bits of information, which were previously limited to 0 or 1, can now be 0 or 1 or both at the same time. So it's no wonder that when we try to model our quantum world with classical computers, we quickly reach the limit of what they're capable of. We need a better tool. We need quantum computing. So in quantum computing, our bits of information are simply called quantum bits or qubits. And our qubits can be any quantum mechanical system with discrete energy levels. So there are a lot of choices for qubits. I'm going to tell you about one particular one that we're studying right here at the University of Washington called trapped ion qubits. So for the rest of my talk, I'm going to explain our particular qubit of choice, Ivory 1.19.19, tell you how we trap it, and finally, how we cool these ions in order to be able to use them for quantum computing. So, barium 138. If you remember your periodic table, barium is in the second column, which means it has 2 valence electrons, typically. And those valence electrons are orbiting around and hanging out. But at this point, I'm a very balanced atom. I have 2 electrons, I have some protons floating around, and everything's cool. I don't want that. I want to be ionized. I want to get positive. So the first thing I need to do is get rid of one of these electrons. The way that we do that is we shine a really powerful laser on it, and one of those electrons absorbs so much energy that it's no longer confined by the nucleus. Okay, so now I'm positive. Yay! All right, now that we have an ion, it's really easy to trap because ions are very sensitive to electric fields. So remember that like charges repel one another. So if you put me inside of a room with positive walls on 2 sides, I'm going to be repelled from those walls. So in this scenario, I'm going to try to get to a negative wall. If as I approach that wall, we quickly switch up the scenario, now I'm going to be going towards a negative wall on the other side. So if we switch this fast enough, I'll just kind of get jostled around in the middle. This is actually how we trap ions in our laboratory. And you might imagine that we do this with a very sophisticated scientific equipment. And we do, but you can also do it in your garage if you just have a high voltage oscillating source and something charged, like maybe some little styrofoam or charged dust particles, and some kind of electrode. So this is a video of just that. 5 tiny little ions, not single atom ions. And what is this scientific apparatus? You too can do this. All right, so once we've trapped our ions, we want to cool them down. All of this wiggling motion and jostling around is not very useful to us. So cooling down essentially means slowing down in physics. In order to do this, we use perhaps what is the coolest tool possible for cooling. We use lasers. Laser cooling, which sounds so weird, but I'm going to tell And you only need to remember two things in order to understand how laser cooling works. I'm going to explain them to you right now. The first thing you need to understand is the Doppler effect. We've seen these signs. It's the same thing that when you're out on the street, the cars go by, they go, meow. Okay? So what's happening here is as the vehicle is approaching you, you can think of those sound waves as getting squished up and compressed. They're shifted to a higher frequency, or blue shifted, because higher frequency is more energetic, and so is blue. On the other side, as the vehicle is moving away from you, you can imagine those sound waves getting stretched out. And that means they'll have a lower frequency, and they're less energetic, so we call that redshifted. That's the first thing you need to know. Got it?
Yes.
Okay. Second thing we need to know is about barium itself. This is barium's dating profile, I think. The only thing you need to take away from this is that it has a very particular favorite color. Blue, but not just blue, 493 nanometers. The reason that it likes that color is because of the energy structure of the atom itself. So typically, this electron is floating around in the ground state. But there's another state up there that the electron can jump to called the excited state. And the energy difference between the ground and the excited state happens to be 493 nanometers, which is right about there on the visible spectrum. So, how does this work? If I am your ion, and I encounter my favorite color, blue, something's going to happen. What's going to happen?
Excited.
I'm going to get excited. And then my electron's going to be way out here. And after some period of time, I will re-emit a photon, send it back into the world, and go back into my ground state. Okay? Those are the two things you have to know. Are you ready to put it all together?
Yeah.
All right. So, we've got our ion. Where's our ion? There's our ion. Our ion's moving around. Remember, we need to cool it so it has some motion to it. Let's say it's running in this direction. The next thing we're going to do is shine a laser on that ion. We're going to choose a very particular color, not its favorite color. We're going to choose something so less energetic than its favorite color. And the reason is the Doppler effect. Because as that atom is going in this direction and the laser is coming in this direction, I'm going to see that light as my favorite color. It's going to be blue shifted, which means it's going to be closer to resonance, my favorite color. I'm going to absorb it, but that photon also has momentum. And that momentum is going in the opposite direction of me. So when I absorb that momentum, I slow down. This is what we do in the laboratory when we cool our ions. It's very effective. Here's some numbers for you. You can go from hundreds of miles per hour to less than 1 in 0.01 seconds or less. That's crazy fast. So when we do this in a laboratory, it looks slightly different. We have it set up something like this, but when it all works, we have systems that can produce single ions right there, that tiny little dot. And I'll zoom in for you. It still just looks like a tiny little dot. So in my group here at the University of Washington, we are studying not only single ion quantum computing and other information, but we're also studying larger qubit groups, such as this one. These are 10 individual barium ions trapped. And when you add more than one, they will crystallize because they repel each other. So they want to be in the center of the trap, but they also don't want to be too close to their neighbors. So they form these very beautiful structures. Each of these ions is a qubit. And so each of those ions has a ground state, an excited state, which we can call 0 and 1 in our qubits. And we can control whether it's in 0 or 1 or both using lasers. So that's all I have time for today. I just want to put up the names of my group members who have helped produce some of these beautiful images. And thank you so much.